Now this is the bread and butter of organic chemistry. And I've already talked to you guys about this. You actually have these beautiful flashcards that you should be utilizing at this point. Have you been utilizing them? Nein? That means no in German. What was that? He said yes. Oh, I thought he said nein. I'm like, that means no. So you guys have been utilizing them? I strongly recommend that you at least open the packet and take a look at them. Okay. Mine are all out of order now. Your flashcards have a lot of the reactions that you need to memorize. And they're not necessarily always intuitive how things are going to be behaving. Okay, so it's going to be essential for you guys to get that in your head because you're expected to know the mechanism. Okay, are we kind of clear on that? Good. Okay, so let's talk about it, right? Okay, so when we start looking at it, we're in the process of alkenes, right? We've been talking about alkenes. We've already talked about alkanes and how alkanes can react. But usually alkanes are going to require you to do substitutions and things to that extent. Well, alkenes are actually going to be breaking up some of your pi bonds. So in this case, this is what's happening, is that we have our pi bond, right? And so this guy consists of a pi bond and a sigma bond. A double bond is consisting of a pi bond and a sigma bond. So what's happened is that the arrow basically shows you where the electrons are going to be starting from and where they're going to be going to. So basically we have electrons. Electrons are going to be transferring from our pi bond to first the hydrogen in this case, or our partially positive moiety. Okay, so then that means that this bond is going to be broken, and then the first thing that's going to be made is a connection with that hydrogen, and so then we're going to get a sigma bond produced as a result of that. Okay, so we're going to be looking at electrons being transferred, right? So the electrons are being transferred from that pi bond to the hydrogen to allow for a new bond to form. Okay, so that new bond forms. That means that this guy now has a positive charge associated with it because you basically removed that electron, one of the electrons, right? So you're replacing one of the electrons here. So electron goes here, then it goes here. Okay. Okay, so we got a new pi bond, and then we got a bromine ion or bromide ion. Okay. Okay, so then that means this, we have plus charge here, minus charge here. So in this case, now these guys are going to come together, and then they're going to form another bond, another sigma bond. Sigma bond. Okay, and so now we have the bromide. Okay, so one gets the hydrogen, and then one gets the bromide. Okay. Okay, so this process of using, this is called the curved arrow approach, right? So the curved arrow basically shows you where the electrons are going. Okay, so again, electrons from the sigma bond basically attacks the hydrogen on the hydrogen bromide. The hydrogen then forms the electrons from the pi bond attacks the hydrogen on the hydrogen bromide, the hydrogen then forms a sigma bond, and then the bromide gets the electron transferred to it. Okay, so then that bromide now has a negative charge associated with it. It's able to sit there and interact with that positive charge, forming a covalent bond. And then we get the bromide attached to it. Okay, forming another sigma bond. Okay. And so, first one, right? Let's see. Nomenclature. I had these separated at one point based upon the actions. Oh, by the way, can you guys tell me the difference between an electrophile and a nucleophile? Which one is which here? Okay. And you're okay. And is that the only thing, if I remember correctly? Okay. So in this reaction, which one is going to be our nucleophile? What's that? Okay. And our electrophile? Are you sure? It says right there. What was that? Okay, so our nucleophile is going to be the double bond, right? Or the thing that has our pi, the pi bonds, right? And then the electrophile is going to be the hydrogen. Okay. Bromine does have lone pairs, right? But those lone pairs aren't going to be utilized for anything. So bromine is only, you think about what's going to be able to react. So or I should say lone pairs. Yeah, that's true. Bromine does have lone pairs on them, but they're not going to be able to utilize those lone pairs. Those are only reserved for bromine. Bromine is not going to get rid of them, right? And so when they make reference to that nucleophile, those lone pairs, they're making reference to those lone pairs being able to be utilized. So like for instance, because if we had the bromine ion, it has lone pairs associated with it, right? And we also have that negative charge associated with it. It's not going to try to utilize those lone pairs for anything. And if it, like say for instance, here we go. Let's see. Where's my nitrogen? Where, okay, here. Because of the characteristics of nitrogen, right? This lone pair is going to be utilized, okay? Where in this case, these both are negatively charged. It's going to use the fact that it's negatively charged, not its lone pairs to cause it. Because chlorine likes to have those electrons around it. It just needs that one electron, right? So it's not going to give up those electrons around it to share, unless it absolutely must do that. And in most cases, it won't. Can you guys hear me on the other side?
Yeah.
Fluorine is even worse, you know, because fluorine is, yeah, fluorine is the bully, right? It's going to be like, no, only wants me around it. So all the ones that are in basically group 17, they're not going to want to give up any of the electrons that it has surrounding it unless they absolutely must. Does that make sense? Okay. So here, these guys have a pi bond, right? That is going to be willing to get rid of. Okay. And so, and then when we talk about the electrophile, positive, partially positive charge, or incomplete octet. So this guy, right? So nucleophile, electrophile. And then we made the bromine, right? The bromine is now the nucleophile, right? So we see that transition, okay? Okay. Let's see, so we talked about that. Okay, so in the case of, let's say, did I screw up here? Okay, so we're looking at two different reactions, right? So in this first reaction, we have a moiety basically acting on itself, right? So let me clear. Okay, so the electrons from this negatively charged oxygen are then going to be transferred to this bond right here. So then that's going to cause us to form a pi bond, right? And then this guy is then going to be transferred to this guy. So then we're going to get the bromine ion. So basically, the electrons are being transferred here and then here. Okay. So in this case, we're going to form, what is this guy called? If we have double bond CRR, I think we've talked about this before. What was it? It's in, no, ether is, there we go, it's a ketone. This is an ether, right? And then an ester is this. Do you guys have your periodic table? I have my periodic table. No, I don't. The packet. Did I give you guys the packet with everything? You guys at home? right? So these are all of the functional groups. At this point, what you guys need to be going through, you need to go through, check off, because all of the functional groups that we've talked about up until this point is going to be fair game, right? So you want to make sure that you have those functional groups, at least being able to identify them, because some of them we haven't talked about how to name them. Get to that point. Okay. 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 So in the second case, so we have water that's acting on this moiety here. So oops. Okay, so I guess this would be an alcohol that's been modified. So okay. So basically, if we have water that's going to be acting on this, then we would end up with an alcohol and then the hydronium ion. Okay, and that kind of makes sense. This guy is plus charged. It's going to be willing to give it. So the lone pairs are going to be transferred from this guy. So do you guys remember when we talked about Lewis bases and acids, when we were talking about electrons moving rather than the proton, right? So in this case, we want to look at things as terms of electrons moving, right? The movement of electrons. And so the electrons here are now going to be used to release the other hydrogen, right? So then these electrons allow for the releasing of this hydrogen, and then that hydrogen is able to sit there and interact with the water. Okay. So as a result of it, like I said, we would get methanol. Right? Okay. Now, the key is we don't want to make the mistake. We want to make sure that we're using the electrons from the nucleophile or the electrophile. Okay. So we're going to be using the electrons from the nucleophile, right? So electrons are coming from our nucleophile, and then they're acting on the electrophile. Make sense? Yeah. Okay. So the nucleophile is going to have the electrons available, right? The electrophile are going to be wanting the electrons, right? Electrophile, what does a phile mean? What does it think that means? Or phil, electrophile, nucleophile, electrophile. What was that? Want, right? They want or like, right? So this guy likes electrons. Nucleophiles, they like nucleus. So electrons, if we think about the nucleus, protons and stuff like that, okay? So this guy is like protons, this guy likes electrons. So these guys are gonna wanna get the electrons, okay? So the electrons are gonna be transferred to these guys, okay? Does that make sense? Okay, these guys, okay? The nucleophile transfers electrons, okay? Electrons being transferred to the electrophile, okay? Well, see, but the problem is that in this case, we take a look at what, let's say this first guy. Well, you have both happening here. You have the electrophile and the nucleophile being on the same moiety, right, on the same structure. And but who's going to be transferring things, right? So we know that In this case, this guy's going to be our transfer, right? Because we know that these aren't going to be transferred because where it's located at on the periodic table. And so we have to use what we know a little bit about chemistry already and say, okay, so that means that we can use these guys. Now, in terms of what we know, location and things like that, we know that bromine doesn't like to be in the center of an atom. It will be if it absolutely must, but usually it's being forced by something that's much, much stronger electronegative. Right? Now, oxygen is strong electronegatively, but oxygen is cool with, like, hey, let's go ahead and break that bond because I know I can make a double bond. Where bromine prefers not to make a double bond. Okay, and we know that, right? So even when it bonds with itself, it's always a single bond, right? So we want to take a little bit of our innate knowledge, the stuff that we already know, what we learned in chemistry already, and use that to kind of lead us in directions. Okay. So here's another example. Okay. So in this case, we have our hydroxide ion providing the electrons. Okay. So the electrons are then moved over to this hydrogen, right? So then that hydrogen then transfers the electrons over to the oxygen, right? We get the formation of water, we get this, which makes sense, right? Because where are we going to get it from? We could try to get it from here, but we know that more than likely it's a lot easier to get it from that hydrogen because that bond is going to be a little bit weaker to attack compared to the double bond here. Okay. Make sense? Okay. Yeah. Yeah. So you want to use what you know and then also what you're learning, right? So the definition of an electrophile, right? The definition of a nucleophile. So figure out which one is going to be playing which character, which role they're going to be playing. And then you start thinking about where is the logical place to attack. Well, we know this guy, hydroxide, right? We know hydroxide. Anytime that you have an hydroxide ion, it's going to try to get to water, right? Okay, so then that means that you're going to end up with this going to be is going to be the, what is it called, the conjugate acid, the conjugate base, and then the other guy's going to be, water is going to end up being the conjugate acid, right? You guys remember that, conjugate base, conjugate acid. Okay, so again, you're going to use what you know to figure things out. Okay, now the key is that so as we go through this process, in this case, this is a different one, right? So we have the electrons being transferred, and so I have the option of going here, I have the option of going here, I have the option of going here. So its attack is going to be on that carbon. That carbon, then those electrons are going to then be transferred to this guy, right? Then this guy is going to get a negative charge. We're breaking that double bond. Right? And part of that is due to accessibility. You no longer have that hydrogen here, right? Instead, you have a carbon here, right? So the difference between this guy versus this guy, right? So this guy is called what again? No. That is the ester, yes. And so again, when in doubt, try to get used to looking at your table on the back because that's going to help you figure it out. The more you see it, the more you get used to it. So this is an ester. So because of that carbon on that ester, then that makes this carbon where the electrons are going to be transferred to. Then these electrons from here are now going to be transferred to here, right? Okay, and so as a result of that, we're going to end up with a negatively charged, let's see, what would be this guy? It would be there. Well, it doesn't fall into one family group right now. It's a little complicated, but we also get a couple of things out of it. We get the OH bonding directly to that, right? And we also get this moiety, right? The negatively charged. So that negative charge has now moved on to the oxygen membrane, okay, by this guy physically attaching itself there. Okay. Okay. So again, we've done this one already. So the correct way of doing this is double bond going to the hydrogen, going to the bromine, right? We get the formation of this, and then this guy is going to form with that guy later for the second reaction, okay? Okay, so let's see if we can get this correct. Okay, so we have our so what is this guy called? What family does it belong to? Was that carboxylic acid? Yes, carboxylic acid. I thought you did say acid. Is that what I heard? No. What did you say it was? Oh, ester. No. Carboxylic acid. Carbon, OH here. So this makes it that acid, right? Because the hydrogen is going to be used for donation, right? Okay, so then what's going to happen? Where are the arrows drawn? Who's going to be donating to what? So who's going to be the nucleophile? And who's going to be the electrophile? This one, okay, nucleophile. Okay, nucleophiles do what? They're going to transfer electrons. I can spell. And the electron, the electrophile, is going to do what? It's going to want to accept the electrons, right? It wants electrons. Okay, so who's going to be providing our electrons? Okay, so the double bond is going to provide. So is it going to be our double? Okay, so you're saying the double bond is going to give it to the oxygen. Well, usually for that to happen, it needs to get it from somewhere. Somebody needs to be providing it. So in this case, it's actually going to be the lone pair off of the oxygen that's going to be providing it. So these guys are going to provide it too. And you're right, the hydrogen, right? Okay, so then it provides it to the hydrogen. And so what's going to happen in that case? Well, we already know what's going to happen in that case. One more arrow is going to happen. So you said the double bond is going to give its electron to the oxygen. Okay, so this is the product of what we get, right? So we end up getting water. So where's the other arrow going to go? Because these are two steps. I should say this one is two steps. We're going to do an exchange. Well, what do you mean? Okay, so you're saying this guy's going to get the okay. So we're going to get the hydrogen. Okay, and so that's how we ended up with this. Okay, so but what's going to happen? There's one more step that needs to happen. One more arrow that needs to take place. Okay, so this guy's going to give it to the hydrogen. Then the hydrogen is going to do what? It's going to give it to the oxygen so that then we could form water, right? So it releases water as a result of that. The hydrogen now is attached to this molecule, right? Because if we look at this guy, right, we know that water has two lone pairs. So that means that it's getting the lone pairs from the electrons that are being transferred. Its second lone pair from the electron being transferred. Right? Because this hydrogen is going to be taken up by this guy. It's getting a second lone pair from that. No, you break the double bond when it's just carbons only, right? And so it's when it's oxygen, it depends. Okay, we can break it with the right targets, right? So if we had something that was transferring electrons here, that would allow us to break the double bonds, kind of like what we saw in the last example. Let me go back so you guys can see. Let's see. Okay, so here we had electrons now attacking this carbon, right? Because it's not going to do anything here, right? It's not going to remove anything here. It's not going to take anything from here, right? So it's going to attack the carbon. So then these electrons then are transferred to the carbon. That causes these electrons to be transferred to this oxygen, causing the double bond to break. Now that the double bond is broken, right, then, and I should say, this whole thing is being added on here. Now that the double bond is broken, then we have an additional oxygen that's added onto here. So that negative charge that we got from here is now being contributed to this oxygen and also led to the breaking of that double bond. It depends on who's going to be the nucleophile and then who's going to be the electrophile, right? So who's the nucleophile in this case? I'm sorry. Who is the nucleophile in this case? Is that really the nucleophile? Yeah, but that doesn't necessarily, okay, so every reaction there's going to be a nucleophile and there's going to be, or and sometimes they're within the same thing. There's going to be an electrophile and there's going to be a nucleophile. Okay, so in this case, who is the nucleophile? Who's going to be providing the electrons? I know the thing keeps coming by as soon as we start talking. It's like he's just having a good time back there, isn't he? Yeah. Okay, so electrophile wants electrons, right? So first we've got to decide who's going to be the nucleophile and who's going to be the electrophile, right? So in this case, in this reaction here, and every reaction is going to be a little bit different depending on who's present. okay? So in this case, who's going to be the nucleophile and who's going to be the electrophile? Because if you looked at, let's go back to the very beginning when we were showing the different possibilities for nucleophile and electrophile. If we looked at it, right, we had cases where we had ones that could fall in either category, depending on what we're looking at, right? So nucleophiles, negatively charged, lone pairs, pi bonds. Okay, negatively charged, right? Lone pairs, pi bond. Okay, so those guys are all going to be possible nucleophiles, right? What you're saying those lone, because we have a double bond in the oxygen. Now, the double bond between oxygen and carbon is different than the double bond between, although it is a pi bond, right? We know that it's a pi bond, but how it behaves is going to be different than what you get with the carbon and carbon double bond, right? Which one do you think is going to be more apt to stay together than to go apart? The oxygen, okay? Because it wants to make sure that it gets its octet and keeps its octet, okay? So where the carbon, you know, of course, it wants its octet, it wants to keep its octet as well too. But if it has a choice, if we have choice between carbon, double bond of carbon or carbon double bond of oxygen, that's going to be apart, okay? Mm-hmm. Exactly. Carbon prefers to have that 4 attachments if it can have it, right? Okay. So the electrophile, so those guys are going to be H plus anytime that we have positive, where we have partial positives, or where we have incomplete octets. Okay, so those are all examples, partial positive. Okay, but again, here, partial positive. Well, this is partial positive, that one's partial negative, right? So, okay, so in this case, this guy is our nucleophile, right? This guy is our electrophile. Okay, so it has the option. It could attack this center carbon, or it could attack this hydrogen. The hydrogen is a lot easier to go after, right? Because it's there. It's just a hydrogen. Okay. In this case, we have it. We have, again, this guy is going to be our nucleophile. It's going to go after the center carbon, right? Because this oxygen is attached to a carbon here. Okay. And then it's going to go after the center carbon, and then it's going to cause the electrons to be transferred to the oxygen, giving our oxygen a negative charge. And then that OH is going to remain attached to that center carbon because carbon likes to have those 4 attachments. Okay. So in this case, which one is going to be my nucleophile? And which one is going to be, what was that? For A. Okay. Let's go back to our definitions here. Yeah, don't look at me because you can't just look at the double bond. Okay, these are the definitions of a nucleophile. Okay, negatively charged, lone pairs, pi bonds, right? Okay. Now, electrophiles, positively charged, partially positively charged, incomplete octet. Okay, so I forget where we're at. Okay, so which one is going to be our nucleophile. The first reactant, right? So, because we know the electrophiles are going to be positive, okay? So this guy is going to be our electrophile, right? This guy is going to be our nucleophile, okay? So nucleophiles are providing the electrons. So where are we going to get the electrons from? So you're saying we're getting it from the hydrogen, okay? So we could, you're saying, now this is what you're saying. You're saying that we're going to take this hydrogen and we're going to attach it to here. That's what you're saying. Is that what you're going to do? Right? Can oxygen have 4 hydrogens attached to it? No, it's not going to want to do that, right?
It will just be
Okay?
the oxygen.
So remember, think about what we're capable of doing, right? So instead, and we also know what we're going to get. We know that one of them is going to be water. So then that means that who's going to be transferring electrons? Where do you think the electrons are going to be transferred from? Yes. Okay, so we know that these guys, you're not going to want to transfer them from here, right? Because usually these guys are going to be ones that want to either accept it, you know, so that you're either making a water moiety or something, or like circling, it's not one there. So these guys are going to either want to accept it or not. So what we're going to be looking at is the electrons here. Okay, so these electrons are then going to, as I said, you guys attack that hydrogen, right? Because what does it have to attack? What can it provide? So if we provide that hydrogen, so we basically remove that H plus and we bring it on to this guy, right? Okay, so then that H plus, bringing it on to this guy means that now we have water. And we're cool with water being formed. So then the H plus is here, and we have a double bond still bonded because it's H plus. Does that make sense? Okay, so then that's the first one. And then the next one would be on to the electrons are being moved on to the oxygen. I should do it now like each other. Like this. Okay. So those would be the arrows for the first one. Okay. Now what about the next one? Okay. Are you sure? Okay. I'm just asking you. Okay, so it's clear here that we're getting rid of the pi bond, right? Because it shows this reaction. So that means that the electrons are going to be transferred from this guy to this guy, right? So then we're going to get the formation of this guy. And then we also get our plus charge added on, right? So then it would be orange. Yes, so you're going to have both your reaction and your products, and you're going to have to draw the arrows. But actually, if we take a look at this, right? So let's look at this. Okay. So we know that the electrons are going to this guy, right? And so there's technically, it's like a two-stepper, right? because then the electrons allows for the bromine to be made, bromine ion, right? And so then that bromine ion then is able to sit there and attach itself as well to that. Okay, so then it loans its, okay. So really what we get is we get the breaking of this guy, we get house structure, ring structure, plus Br, and then this guy lines the back, right? So we get that guy formed, right? Although it still will be plus, that's technically, so we get plus, fortunately. Plus, and then we get this guy. Sorry, this guy should be plus. Then we get this guy coming back. Because this guy is a Br minus, I mean a Br plus, right? So very first ones are going to be transferred here. So you have your 2 electrons that are being transferred here. It has 6, right? It gives this guy a minus charge. This guy becomes a plus. It gets the plus that was given here. And by it giving up the electron, it gets that other plus. Then it comes back and gets it. Its second step would be the reattachment of the bromine. Does that make sense? Okay. What about this third one? Okay, so this guy's our nucleophile. Okay, so what was that? Okay, so okay, so you remember, you guys are going to have to be a little bit flexible. Where's the double bond located? It's between the oxygen and the carbon, right? So if we have to use it, we can use it, right? But that's if we have to use it. In this case, it's clear that your negative charge is going to be your nucleophile in this situation. And then, so the hydroxide is going to be our nucleophile. And then, so you guys you're looking at things as absolute. You guys got to stop that. That's not going to, if you look at things as absolute, you're never going to, you've got to be flexible. Okay. So you got to go with some flexibility. Okay. So you have to look at the moieties that we're looking at, right? What is the most likely? What is going to be the most likely nucleophile? What is going to be the most likely electrophile, right? Because it's going to be relative depending on circumstance, right? So here we have a hydroxide group. It's a minus charge, clearly a minus charge. Yeah, it's going to want to be able to transfer electrons. So if we transfer electrons, who are we going to transfer to in this case? The oxygen without the double bond. So we're going to transfer it here. That's right. Okay. Okay, are you guys with me? Okay, so then in that case, that means the electrons are being transferred here. This guy gets that negative charge associated with it, negative charge, and that hydrogen becomes released to make water. And this is the reason why a lot of it is going to be memorization. We're going to start talking about names of the specific reactions. But the thing that you want to understand is that things are going to be transferred. Electrons are going to be transferred. Sometimes you're going to be breaking the bond and forming water, right? If you can get water out of it, that's usually a good thing. Sometimes you're not, okay? So it depends on where it is and what it's attacking. Does that make sense? And it also depends on, because we have another example of this, right? When it was, I hate this, when it was a carbon chain here, it becomes less attractive to attack, okay? Because the carbon chain that's there, okay? So then it attacks this carbon, okay? The hydroxide does, okay? So you guys are all kind of, okay. Let's see. So let's look at it like this. Yeah. Yeah. Okay. So let me show you what's happening. Okay. So in this case, so if we have carbon double bonded to, and I'm just going to draw that as a stick structure, right? And then we have okay. So what's happening is that we're taking this. Okay, we're taking this guy, right? It's taking its 2 electrons, but in different colors. It's saying, okay, it's taking its 2 electrons and it's donating these electrons to this guy, right? So the donation of these 2 electrons means that now we have this H plus that's being released, right? And it's going to be attached to this guy, right? So then we get the formation of no, okay? It doesn't walk away with it, but it breaks this bond, right? It causes that proton to be released, right? So then so you got to think about it, electrons and protons. So you have both of these things going on. So remember when we were talking about acid and bases and everything like that, proton donors, electron donors, but we're taking a look at it as in terms of just the electron, right? So in this case, electrons are being donated to the acid, right? This is the acid right here. So the hydroxide is donating its electrons to the acid. Okay, so acids are electrons acceptors. So this one is pretty straightforward. So as a result of that, we're going to end up with water and we're going to end up with a conjugate base, right? It normally would be a salt, but this hydroxide is only hydroxide. We don't have any sodium that's attached to it. Okay, so that means that this negative charge is now being transferred over to here, right? Because this guy now has that water balanced out. We have to keep track of the charge overall. Okay, so that means 2 electrons are coming over here. Okay, so 2 electrons come over here. That means that this guy is free and is able to bond with the water. Okay, so then that means that as a result of that, we're getting, write this in blue, we're getting this. Because those 2 electrons were donated to us. You guys can see my dots there. Can you guys see that? Okay, so those 2 electrons now, and this also is a negative charge, right? Okay, you guys have that look. I'm not convinced. That's right. So you broke the bond with the H. You allowed the H to be released and added onto the hydroxide. So it forms water, right? 2 electrons. That means that one of the electrons is that negative charge that we're getting, right? So it's that negative. And then the other one kind of gives us the second one. So then that means that it's able to sit there and form that bond, reform that bond with the other hydrogen, right? So overall, neutral charge, negative charge. So overall, there's no change. We're still keeping an overall negative charge in this thing. Over here, this guy has a negative charge. It still balances out. Are you guys with me? Okay. So Pula is
Yes.
okay. So just a whole bunch of homework assignments. That's what I'm saying. I'm here. Oh, okay. But don't you guys work as a class and when you guys do homeworks? Oh, you need my guidance, is what you're saying. Okay, so in this case, second last one, I mean the very last one, who's going to be the nucleophile? Okay, so put it in. And who's going to be the electrophile? Okay, and this is an easy one, right? Right. So that means that the chlorine here is going to be adding or transferring its electrons here, right? Now this is pretty simple. Minus, plus comes together, form one unit, and we get it together. And for letter C, yes, because it's going to be going off of it's breaking the bond between the hydrogen, causing just that one. Yes, so it's a single arrow. Where letter B is kind of like, it really is a two-stepper, but I guess you could make it as one arrow as well too. So, and then this guy's a 2. It goes to the H, then goes to the, because it's picking up the H, and then it's transferring the. So. Okay. Okay, so let's see. Let's go to another topic. Okay, so when we talk about, so this is basically is a reaction coordinate diagram. It kind of shows us how reactions really occur. And this is not a really the best diagram shown ever, because usually the way we look at it, and it's really hard to see in this case, but I'll try to point it out best I can. Okay, so this here represents the reaction initially, right? It has to go over a hump. This is called your transitional state, right? So you have to put out so much energy to kind of get it to happen. And then this is what you get at the end, okay? Now, the reason why I say this is not the best diagram for this process is because usually, I'm drawing this line here, is because the energy in your reactants is going to be lower than that in your products, right? And that's what drives reactions, okay? To kind of keep them stable. So that's the progress of a reaction. So basically, we have A and B interacting. We have our transitioning period where we have A, B, and C all interacting together. And then we have the bond being broken between the A and the B, and instead we get development of B and C. Okay. This here represents the free energy, the energy associated with this process. Right. As I said, this requires us to get to a certain energy point. So a lot of cases you have to put energy in to get that reaction to happen. And then this here is the free energy of those products. And typically the free energy of the products is lower than that of the reactants. Okay, and that allows the reactions to be stable. If it's not lower than the reaction, chances are it's never going to make it up that hill. Okay. Okay, so now the key to this is that it takes energy to get to each of those steps, right? It takes energy to be put into this transitional state. This state is a transitional state. It won't stay at that state, right? It shouldn't stay at that state, okay? Because it needs to go down that hill to get to that reactant, okay? So it can be a stepwise process, right? Or it can be, sometimes we see it as more of a direct, where we don't show that transition state because that state happens very fast. Okay. Okay, so this brings us to the last things that I think both of your classes or all three of your classes had talked about, or all two of your classes. I'm trying to think how many different generations I have in this class. So you guys are the same. You four are the same generation, and they're the same generation. So 2 generations. Okay, good. Okay, so thermodynamics and kinetics. Okay, so we're going to be talking a little bit about equilibrium. We're going to be talking about thermodynamics, and we're also going to be talking about kinetics. They're all kind of tying together. And now you're going to get a little bit more than what you guys got in 1B. Okay. Okay, so you guys remember this process? So thermodynamics basically deals with the transfer of energy that's going to be associated with it. So even though it says how much Z is formed, it's how much Z is formed at what cost energetically, right? Or how much is going to be produced, okay? Because we know that nothing comes for free, right? Okay. So we know that everything is going to cost us a little bit, okay? So, and that's the key that we want to keep in mind. The other thing is how fast is this going to react? How is it going to happen? How fast is it going to happen? Is that transitional state, are we going to be able to observe that transitional state, right? We'll see that intermediate product and then see that final product, okay? So let's start off with the kinetics, or we'll say the equilibrium. We'll start off with equilibrium, then we'll get to the next. So you guys remember the equilibrium constant is going to be equal to the products over the reactants, right? So this here is just a generic diagram so that we know that KEQ is going to equal the concentration C, the concentration of D over concentration of A and B, right? Okay. And we know that we know the rules that it has to be dependent on either molarity concentration, so it has to be aqueous solutions, or it has to be, what else? Anyone else? Yeah, or gases. That's right. Okay. And do you guys remember why that's the case? Let's see. So if it was a solid, why can't we take solid into consideration? And why? Okay. So in the case if we put a solid of whatever it is, it's a solid, right? So then the reaction is only going to be dependent on the liquid around that surrounds it, or the gas that surrounds it. it's not going to be dependent on that solid because we have all this stuff that's in the middle that we can't get access to. Okay, and that's the same thing in the case with the liquid, because usually if it's a liquid that's kind of sticking together, we're only going to have access to that liquid at that surface, that interface between the two liquids. You guys have been playing with solutions that have interfaces, right? How much access does the solution up top have to that solution at the bottom? Let me give you, I said you guys have been playing with solutions that have interfaces, right? So let me draw this out. So here's a test tube, right? We're talking about organic chemistry, right? We have a solution that is organic and very hydrophobic. And we have a solution that is aqueous. Okay, now we have something in the solution that interacts with this organic moiety. Now, if my solution is aqueous, how much interaction am I going to have between my aqueous solution and my organic solution? Where's that interaction going to take place? It's going to take place at the interface, right? So that means that I only have one layer where a reaction can take place, right? So it's not going to be dependent on how much of my organic component is. It's only going to be dependent on that interface, right? And so that's the reason why we can't take in consideration the liquid or the solid. Okay, so that's the same thing if I had a cube of or a circle of metal that I dropped in my solution, right? It's only going to be taking on place on the surface. So it's only going to be dependent on the solution and that interface at that surface. Right? Yeah. That's right. It didn't give us as much smoke as we wanted to because the water surrounded the dry ice and froze the dry ice in the middle, right? So then that way we were just limited by that because we couldn't get complete access. That's exactly it. Good analogy. Okay, so let's start talking about that. Okay, so let's. Okay, so we recall the equilibrium constant, and we recall that this is the equation for it, simple equation. So this is an example of exergonic and endergonic. Exergonic reactions is basically when our reactions are going downhill. Okay, so in other words, our Gibbs free energy is going to be a minus value. So in other words, the reactants, the energy associated with the free energy associated with the reactants is greater than that of the product. Okay. And then this is an example where of an endergonic reaction. In that case, the energy associated with the reactants is greater than that of the products. So you get with a positive delta G value. Okay, and Gibbs free energy is going to be the change in the free energy associated with the products minus the energy associated with the reactants. And we want that value for it to happen spontaneously or to happen naturally. It needs to be an exergonic reaction. Okay, or we're going to have to make up for it in another way. Okay, we'll talk about that, I promise you, in a minute. Okay, so Gibbs free energy can be associated with the equilibrium constant, or is associated with the equilibrium constant. And the way it's associated with the equilibrium constant is delta G naught is equal to negative RT ln Q. I mean ln K EQ. Okay, so then that basically means that the equilibrium constant, the value that we get for the the log of the value of for the equilibrium constant times the RT, R being the gas constant, T being temperature that it's at, is going to give us our Gibbs free energy, okay, or that change in energy. Okay. I know it's been years since you guys did that in some cases. Okay, so delta G for the conversion of an axial fluorocyclohexane to an equatorial fluorocyclohexane at 25 degrees Celsius is negative 0.25 calories per mole. Calculate the percentage of fluorocyclohexane molecules that we have. The fluoro substitution is an equatorial substitution at equilibrium. Okay, so what is going to be the equation? Well, what is going to be the chemical equation? Okay, so we have okay, so equator versus axial. What is the distinction between equatorial and axial? Okay, so is it that they're saying the so calculate percentage substitution is going to be, so we have one that's equator, so we have, I know I didn't draw this right for you guys to see it nicely. I should have drawn it as a chair. So, okay. So this is equial, this is axial. Okay, so we know that this is equilibrium. They're both existing. Okay, and you said delta G not equals minus RT. Okay, ln K. Okay, so okay, so what do we know? So if we made the, let's see, I dropped the right way. Okay. So axial would be like this. Equial would be like that. Okay, well, here it'd be the same structure. Only thing it's chapter 2, I believe. We talked about it. That's right, the chair structure. Yeah. So that's what the distinction is. I was being lazy, I already drew it like this. I didn't want to. Okay, so we're just shifting where they're located, how it's going. Okay. So, and they said that delta G equals, well, we know that delta G equals minus RT log EQ, right? They give us a value for delta G, which is negative 0.25 kcals per mole. That's going to equal negative RT. And I'll give you guys the value for R because it has to be in the units of kcals. So I have another sheet that I'll hand out to you guys later on. So I think it's 1.80 times 10 to the -3, I believe. -3. Yeah. Okay. Oops. That's going to equal R. And it's going to be cals. Sorry. Kcal. I'm going to drag this over to the side so it's not so crazy. I think it's 1.980. That's kcal. Kelvin. Okay. And then room temperature has to be in Kelvin. So it's 25 degrees plus 273.15. So that's equal 298 Kelvin. So if we plug that all in, we'll end up with 0.25. And those are going to cancel out, divided by RT, which is 1.8 times 10 to the -3. And that's going to equal ln(k) EQ. So if we take the natural log, what was that? Okay. Two five divided by 9, 8 times 10 to the -3. Oh, sorry, I forgot. 298. Thank you. Because I'm lazy and I didn't put it all in there. 298. So I get KEQ equals 1.53 . Okay, so if I remember my K value, K is going to equal EQ is going to equal the concentration of my products over my reactants. Okay, so my product is EQ for equator, and then axial on the bottom. So basically it's 1.53 over 1. Okay, so then it says calculate the percent. So how would I go about calculating the percent? Okay. Okay. Okay, so my parts being EQ, okay, over axial, okay, equatorial, like equator, equatorial, equatorial. Okay, so then what was that? Equator, it's an equator or yeah, equator. Okay, so that's 1.53 plus 1.53 plus 1 times 100. So that's 60.5%. The R represents, it's a constant, so that's like our gas constant. So we just got to make sure that we have it in kcals moles Kelvin. And like I said, I'll give you guys a sheet of different values of R with different units. I have that somewhere in my stash of files. Okay. How you guys doing? I think it's time for a 5-minute break. Okay. So Gibbs free energy. So when we take a look at Gibbs free energy as a whole, so its Gibbs free energy is going to be equal to delta H, which is the heat of formation, or the enthalpy that's going to be required to break bonds and to reform bonds, right? Minus the freedom of motion, or the entropy. So where delta S represents kind of the entropy. Okay. So if okay, so do you guys remember Le Chatelier's principle? Le Chatelier's principle. Okay, so let's talk about Le Chatelier's principle. So you guys see the equation. We have A plus B. Okay, so let's say I removed D, right? Now, if it's in equilibrium, if our solution is in equilibrium, and I have this little system, I just removed all of the D, what's going to happen? It's going to try to reach equilibrium again, okay? So that basically means that the reaction is going to be driven in this direction, right? You guys remember that? If we're removing D, we're taking D, we're slowly taking D out, we're removing. Eventually, it'll do what I wanted it to do. We're getting D, we're moving it out, right? Okay, so because the reaction is dependent on D, and it has to try to reach equilibrium. So if I take out the D that's being produced, it's going to try to produce more D to balance it out. Okay, so that's Le Chatelier's principle. Because equilibrium means that the equation, that's right, they found a point where they're happy, right? And so they're going to try to keep it at that concentration, right? So if I remove D, then that means that A and B are going to be driven to make more C and D. Okay. Yeah. Okay. So if I increase A, what's going to happen? It's also going to be driven to the product side. That's right. Right. Because we have more A, it's going to push everything. So until it reaches an equilibrium again. Okay. So because we know that equilibrium is a constant, and so we have to try to reach that point again. Okay. Okay. So we can also get in a situation where we have reactions that are coupled, right? And this is what happens quite a bit in organic chemistry, where A makes B, which makes C, okay? Where one of these reactions, that intermediate, can be, let's say, in this case, this is an endergonic reaction. Endergonic meaning what was that? The delta, say it again. Yes, so we have to put energy in to sit there and drive the reaction, which also means that, what was that? What's positive? The delta G is positive, right? So that basically means that it takes energy to get up to the products, right? And then and if you look at the energy from the reactants to the product, it's up higher in terms of that energy, okay? And then exergonic, which means the opposite, right? And then let's say from B to C is exergonic, right? Okay, so our intermediate, we have to put energy in to get to that point. And then to get to our C point, that is kind of like a downward slope, right? So it's easier for us to get there. Okay. Okay. So this is an example of a coupled reaction where you have them coupled to sit there and make something happen. Because usually, like I told you, it's easier for us to sit there and have, say if it's an endergonic reaction, that's really hard to get because you always have to put stuff into it to make it happen, right? You want something that's going to happen more spontaneous, right? Just adding things together, it's going to happen. So coupling two reactions allows us to do that, okay? Okay, so let's see. I hear chat. Let me see the chats. Oh, I can't. That's true. I can't hear you. Why can't I hear you guys?
I don't know. Can you hear us?
Message on the smart board.
Can you hear me?
What was that?
Can you hear me, Dr. Henry?
Oh, before I erased? What did you guys say? I can't hear anything you guys are saying. Hold on. Okay, there's some things going on here. Can you guys hear me?
Yeah.
I can hear you now.
Okay, finally.
Okay. So you guys had questions? I'm sorry.
Yeah, but I forgot what I was gonna ask.
Okay, so I'm gonna keep moving forward then. Okay, now it's not showing up on the.
Wait, Dr. Henry, so for these this last problem that we just did right now, so the small arrows is always gonna be endogenic, I think it was.
Okay, let me go back. Let me see. I don't know what's going on. You guys, I can't see. Yeah, that's not working. Hold on, give me 1 second.
Okay.
While I try to figure out. Now that I got the audio working, now the video doesn't want to work. Okay, so the arrows just basically shows you. So if we take a look at this, it is an equilibrium equation, right? Abby?
Yeah.
So that means that it's favoring going in the other direction. So B intergonic basically means that it would be favoring going in the other direction.
Okay. So basically the meaning of those arrows will never change. They will always be the same.
No, it just depends.
It just depends on what we're given.
Reaction.
Okay.
Yeah, it depends on the reaction. So
Okay.
when it's intergonic, that means that B, it's favoring going in this direction. It takes less energy for it to go. So you're basically going from let me see if I can show you. Give me 1 second. Okay, this guy. Okay, so this guy is endergonic right here, right? Endergonic basically means that it's higher energy for the products than the reactants, okay? So then our delta G is going to be a positive value. Now, since it's an equilibrium basically means it goes both ways, right? So I can go to my products or I can go to my reactants. So it's easier for it to go through the product. So in the case of this reaction that's being coupled, so we have B, so it's easier for it to go from B to A than it is to go from A to B. So it's favoring driving to the other reaction, right? Where the reaction in B is favoring going to C. Okay, so we're basically coupling two reactions to get our C product.
Oh, okay. Yeah, that makes more sense. Okay. Thank you.
Okay, so if we take a look at this, so the enthalpy of bonds being broken, right? So that's your DH basically means it's the dissociation of things. We're breaking the bonds here. So a pi bond for ethane, dissociation enthalpy is going to be 62 kilocalories per mole. The dissociation bond between the hydrogen and the bromine is going to be 88. Altogether, that's going to be 150. So the bonds for formation is going to be for each of the hydrogens. And then altogether, it's going to be 101 kilocalories per mole. And then the bond for formation of carbon and bromine is going to be 71. So the total energy associated with formation, in that case, is 172. So if you get the bonds for breaking and your bonds for formation, so our delta H for the reaction is going to be the bonds for breaking minus the bonds for the formation, and that's going to be negative 22 kilocalories per mole. Okay, so is this a so we know that this is an endothermic reaction or exothermic, since we're talking about enthalpy. Exothermic, because we have a negative value. You guys remember that, right? Okay. Okay, so these are some of the values for bond dissociation. So if you're losing, yes. So if it's a negative, yes. So typically it's a negative G. That means it's exogonic, right? Because that deals with the whole energy. Gonic basically means all energy, right? And then negative G, I mean a negative H, that basically deals with the thermal. That's thermal chemistry, right? So that's heat, okay? And then S is entropy, okay? Negative entropy basically means that it's going to happen spontaneous, right? If it's a positive value, then that means that you have to put a lot of energy into it to make it happen, okay? Have you been crying? Jesse, I'm talking to you. Said, have you been crying? It looks like you have a tear on the side of your eye. Okay, just making sure. Okay, so, I mean, I know it's bad, but it isn't that bad, is it? It's that refresher course of all the stuff that you guys learned in 1B. I know, bringing back those memories, huh? Okay, so if we look at the enthalpy, right, of dissociation, if we break one hydrogen, take off one hydrogen off of methane, it's going to take 105 kilocalories per mole. Now, if we take off one hydrogen off of ethane, it's going to be 101.1 kilocalories per mole. So what do you think is the distinction between what we see here and what we see here? Because they're both removing one hydrogen. Let me draw out the structure for you guys so you guys can see. In this case, we're just removing one bond, one hydrogen, carbon and hydrogen, breaking one of those, right? And then in the other case, we're also just removing one hydrogen. What is the distinction? So it takes less energy. Okay. Okay. And that's sort of what we see. Because if we look at it here, if we add in another carbon, well, it's going to be easier to take off. Okay. So in this case, it's going to be easier to take off that hydrogen, right? Each time, less energy. So we add another carbon, it makes it a little bit easier. Okay. And then, yes. It becomes easier because you have more carbons here, right? So the more carbons you have, it's easier to get the hydrogen off. Right? As we increase the number of carbons, we go from a single carbon to 2 carbons to 3 carbons, right? It becomes, the energy for dissociation becomes easier, less energy. Right? You see that? And that's because in that case, you have those carbons that are interacting with each other, right? And so it starts to weaken the bonds, those hydrogen bonds, because they're not going to be as strong. So it'll be easier to sit there and remove a hydrogen from a longer chain molecule than it is to remove from a shorter chain. Okay. So, and then if we take a look at from carbon to break the bond between the 2 carbons, that's going to be easier than the hydrogen because bonds behave differently, even though they're sharing electrons, right? Because you have carbon, the way that they share is going to be slightly different than the carbon hydrogen, because since the hydrogen has a little more tug than the carbon part. Okay. And then it becomes easier to break bonds between, let's say we break, this is a carbon here, right? Carbon attached to a carbon. It's easier to break this bond compared to when we just had the 2 carbons. Sorry, 2A. See. Okay. So again, as the chain gets bigger, it's easier, starts to become easier to clip the bonds. Okay. You guys falling asleep on me? I know it's not exciting stuff, but it's going to be okay. Yes. What was that? Yep. Okay. And then we also know about the electronegativity, right? So fluorine is more electronegative than chlorine, that's more electronegative than bromine, that's more electronegative to iodine, right? So this guy's going to have stronger bonds, can take more energy to break. This guy's going to take a little bit less. This guy's going to take a little bit less. So as we go down the periodic table, so you guys all remember that, right? Yes, that's right. Bond length and both of those things, yes. Okay, so now this is a issue here, right? Fluorine. Well, that's a lot easier to break than chlorine, and bromine, but these guys obey that rule. So this gives us an exception, right? What was that? It has a lot to do with the bond. They're really tight together and they don't like that. It's unstable, right? For them. So they would prefer to be with somebody else, right? And they're both really strong. So you have 2 really strong people saying, okay, we're going to share. And they really don't want to share. Like share evenly. So if they get a chance to break it, they're going to break it. Fluorine is very reactive because of that. Okay. Oh. So when we start looking at double bonds versus single bonds versus triple bonds. So you guys remember double bond, it's easier to break a double bond. I mean, it's easier to break a single bond than it is to break a double bond. So 90, right? 90.2. If we're breaking that single bond between the two carbons. When it's a double bond, 174, triple bond. Again, the bond lengths are shorter in the case. They get shorter, the more bonds we add it, it's going to get shorter. It's going to be more tighter. Okay. It's also going to mean it's going to be a lot harder to break because it's going to be harder to get in between. Okay. And then this just kind of shows you. So if we have the methyl fluoride, methyl chloride, so these guys behave the same way, right? More energy because now this guy is going to be strong with this guy because it has that room to be strong, right? And it's easy for it to be a bully with somebody who's weak than compared to being a bully with somebody who's strong. Okay. The double bond, except for like let me elaborate on that a little bit. So here, the double bond takes more energy to break than the single bond, right? Single bond, and then the triple bond takes more energy to break than the double bond. Okay, does that make sense? Because you're getting shorter bond length, right? Which means that, yes. This one here? Okay. Yeah, but they're saying the single bond, you're breaking the single bond on the with the hydrogen, not the double bond itself. Here you're breaking the double bond itself. Do you understand? Yeah. In other words, if you're trying to break, and it still means the same. They're saying that the energy that it takes to break this, it's going to be higher than what we saw with the single bond to take off that hydrogen, right? And so here they're taking off the hydrogen off the triple bond. It's going to take more energy to do that. Okay. Questions? No questions? Okay. Okay. So this is called catalytic hydrogenation. Okay. So in other words, we're going to be adding hydrogens, right? And we're using a catalyst. Okay. So in this case, what we're using for a catalyst, we're going to be using, so this is metal and basically carbon, right? So this is PD. PD is palladium. Not palladium, it's palladium. Okay. So they're using palladium metal. So in this case, by using a palladium metal, we're going to end up breaking the double bond and making it into a single bond. Okay. And so you're using the metal as just a catalyst to speed up the reaction. You know what a catalyst is, right? Catalyst. It just speeds up the reaction. Okay. And so we'll go from an alkene to an alkane. So anytime that you see a metal and carbon, and then you have hydrogen present, it's going to just break the double bond, right? Simple. Okay, questions? Okay, so here, I'm going to ask you, who's a nucleophile? Who is the nucleophile? The what? The alkene, that's right. Yep, that's right. So then who's going to be my electrophile? Okay, the hydrogen. Yeah. Okay. Okay. So what alkene would you expect to start? Let's say, what alkene would you expect to start with if you wanted to synthesize methyl cyclohexene? So what is our product, first off? Okay, what does that look like? Okay. Like that. Okay, so what's going to give me that? And what am I going to use? What, if I'm starting with an alkene, what alkenes can I use? Well, tell me what I'm drawing. Okay. So, which one? So we have this guy. So you're saying something like this. Okay. Do you guys agree? Okay. And then of course we have BD/C plus H2. Okay. Would anything else work? Or is that the only one? How about this guy? Would that work? Say no. Anybody say yes? You say yes?
Yeah.
You say yes? So yes, this would actually work because it's going to behave the same way. Where is it going to attack? The double bond, right? So these double washes, the double bonds are going to be transferring. This double bond is going to transfer its electrons to the hydrogen, breaking up that bond, causing each of them to get hydrogen.
So can it work with the double bond is anywhere on the cyclohexane?
That's right. It can work with double bond anywhere on the cyclohexane or the double bond in the stem as well of the cyclohexane. Okay. So we had a lot of options. Okay. Okay, so what's happening? Okay, so here we have a pi bond, right? So we basically allow the hydrogen to kind of get hitched to the surface, right? So by the hydrogen getting hitched to the surface, it then will slowly find its mark on that pi bond, right? The electrons are then going to be transferred to the surface to allow the hydrogens to be moved. Okay, so we end up with the formation. This is our intermediate. Remember, we talked about that intermediate or that couple reaction. So we get a radical form. This represents a radical. So we get the formation of the radical temporarily. That's what's happening here. And then we have the hydrogen radical, which is just the hydrogen itself. And then it forms a bond for stability. Okay, so then we go break up the pi bond to make 2 sigma bonds. Okay, so here are 3 different reactions. Okay, and we end up with the formation of all same thing. Okay, so this guy is 2. So 4 carbon chain with a double bond in it is called and a methyl group. What was that? I said a 4 carbon because that's 4 carbon is the longest chain. What was it called? It would be called butene, right? So this guy would be called, let's see, 1, 2. So this would be 2 butene. I'm sorry, 1 methyl. I mean, sorry, 2 methyl butene, 2 butene. Was that? Okay. This guy here would be 2 methyl, 1 butene. And this guy here would be 1 butene, 1, 2, 3 methyl. You could call it iso too, right? Okay. So the energy, the enthalpy to, or the heat released, the heat of the reaction is, in this case, is negative 26.9. This guy is 28.5, and this guy is 30.3. Okay, so are these created equally? First off, no. Okay. So the one that has the most energy, right? The most heat released is which one? The first, the second, or the third? The third, right? So the third one is going to be the least stable, right? That's the reason why it's going to release more energy. So this bond here is less stable, right? So you're going to have more energy resulting from that because it's less stable. Okay. So third one has less energy. The one that's more stable is the double bond between, or right after the second carbon, right? So this has more stability than this guy or this guy. Well, it is due to the fact that it is unsaturated, that's partially. And then it's also the double bond, because you're burying the double bond between the two, the middle, right? So it makes it a lot more stable on the sides rather than having a double bond on one of the sides or the other side. So if you take a look, both of these are side double bonds, right? So on that first, either the first would be the first carbon after the first carbon, right? In both cases. Okay. So being there is less stable than being buried in the middle where you have 2 carbons on here and 2 carbons here. So a little more stable because you have those carbons kind of protecting in a sense. Okay. Okay, so which of the following alkenes has the greatest heat of hydrogenation? A, B, or C? In other words, which one is going to be more stable? Which is going to be the least stable? Greatest heat, which means the least stable. That's right. Because that's going to give us the most heat, right? Most heat released. That's going to give us the most heat. The least stable is going to give us more heat. This is going to be anxious to get rid of it. It's going to give off more energy. A, B, C, or all of them are about the same, or A and B has the greatest. Wow.
There's more carbon on one side than the other. I know things are A, but then
Yeah.
and so I thought of like,
Steric hindrance. Steric hindrance.
yeah, so like there's no any space.
Okay. So the correct answer is C. C would be the most, have the greatest heat of hydrogenation. And you're right. It has to do with the fact that cis versus trans. Yeah. Being on the same side makes it less stable. Okay. So relative to stability. So if these guys were all the same R group, this is going to be more stable than having 3 of them with the same R group and the hydrogen, or having 2 with the same R group and then 2 hydrogens, or having 1. Okay. You had a question? Scratching your head. Trans is going to be more stable than cis. So if we take a look at the delta H, so this is a trans molecule, so this is trans 2-butene. This guy's going to give us well, it's going to make less heat than cis 2-butene, not by much, but there's a distinction. Okay. And this shows it. So because you have, this is called steric hindrance. right here. So where these guys kind of interfere with each other, that causes it to be less stable. So that means it's going to produce more heat. It's really anxious to get rid of that structure. And the structure itself is already unstable. So where this guy is more stable because of that. Okay. Okay, so trans, more stable than cis, or I guess that's equitable. Right. No, that's there. So axial to each other. So less stable, stable, right? More stable. Okay. Rank the following compounds in order of the most stable to the least stable. Yeah. Abby,
I'm in between two, but I don't know if they're right.
well, tell me what you think.
Oh,
Tell
I'm
me
in
your two.
between. We're going from most stable to least stable, right?
That is correct.
Okay. I was thinking D, but I don't know.
The correct answer is D.
It is?
Yes. Okay, so let's talk about it.
Okay, so
Okay, first off,
oh, sorry.
oh no, go ahead. No, go
So
ahead.
I thought it was D because I think I once said like something about stability, and I was looking at the shape and I was thinking if it can't be like the least stable cannot be 4 because I don't know, like I was just looking at the shapes. Like if it's completely a shape, then that would be the least stable. I think I'm just making my head go crazy right now.
So yeah, 4 can't be the least stable. That's true. We'll explain that why in a minute.
Okay.
So why would it be 1?
I felt like it was the least stable because it's like if you compare it to the other 3, of course, it's like not a full shape.
Okay.
But then
So Sampula said, because you can't hear what she said, but she said because of the angles. So right here we have very sharp angles that are going to be associated with it. You guys remember what the angles are going to be? Yeah. So they're going to be pretty tight. And even though that we know that it's an SP2, which means that what shape should it be? Not that Joe. It has 3 attachments. So if it has 3 attachments, it should be what shape? It should be trigonal planar, but it's not, right? So already we're having the issues with the bond being shorter than what it should be. Trigonal planar should be a 120 angle, right? Okay, so we're already pushing that. The other thing is, isn't this also like a cis structure? Right, so that's even worse. Okay, so it's cis, it's a shorter angle than what we get if it was an open structure, right? So that's 2 reasons already, right there, that makes it worse than all the rest, right? So then we know that this guy's cis, okay? So that means, okay, that's going to be less than our trans. This is trans, right? So why is this one better than this one? Okay. So if we take a look at this, right? Because we have, well, let's figure this out here. So we have one hydrogen that's here, that's also attached here, where this guy has, quote, our two hydrogens, right? Instead, we have these longer chains that are going to be associated with the side. So that's going to add some stability, just having those chains to it, right? So it adds us a little more stability. So we have a methyl group here and a methyl group here, adds a little more stability. Even though we still have that cis-acting type of structure, we have the other side kind of balancing it out. So this guy is going to have more stability than this guy. So then it's going to be 4, 3, 2, and 1. Everybody got that? What you got for your answer? Okay. Okay. Now let's talk about the speed of the reaction. And we got a few more minutes. I'm gonna go 5 minutes and then I'm gonna let you guys go. Okay. Okay, so okay, let me clear. Yeah, because you guys have lab and you're almost done with lab 4, right? You're not almost done with lab 4. Yeah, we still have 2 more parts. Well, yeah, we still should be able to finish because it should take us like 15 minutes to finish, 20 minutes at the most. If not, we're gonna make sure it's done in 15 or 20 minutes. Okay. So if we take a look at so this is the reaction coordination diagram for a fast and a slow exergonic and endomorphic reaction. Okay. So this here represents the delta H. The delta G that has to be. So this this here represents the activation, right? So the energy that's going to be responsible, the free energy that's needed to be responsible for the activation, right? So we got to get above that threshold, the activation point, okay? And then once we get above that threshold, then it's just home selling, right? So we kind of look at it as we have this hill that we have to push our car up, right? So first we have to get up to that top of the hill. It's going to take us a lot of energy to get up to the top of the hill. And then once we get to the top of the hill, the car is just going to roll itself down, okay? So this one is going to be a fast reaction. This here is going to be a slower reaction, right? Because it takes more energy to get us up that hill. So that's going to affect our speed, right? How fast we're going to get up. Although once we get to the other side, it's going to be home selling. But the first part of it is getting to enough energy built up to do it. And so that's your rate limiting part. That activation is going to be your rate limiting. Okay. Are you guys with me? You understand? A is going to give us a fast reaction, where B is going to be a slow reaction because it takes us time to build up enough energy to get over the hump, right? So coming down the hump, it's not going to be the issue. It's going up the hump. That's the issue. So usually the reaction rate is a result of us going up the hump. So it's that activation energy. So when we do our equation, it's going to be based upon the activation energy. Right? So gives free activation. The free energy of activation is going to be the energy barrier, right? So it's getting up that hump. Okay. And that's our delta G is going to equal our delta H, the heat that we need to get over, plus the entropy. Okay. Okay, are you guys with me? 5 minutes. 5 more minutes and I'll let you go, I promise. Because you guys are done at 4:30. Okay, I can't make it 4:30. Okay, so which of the following statements is true? The delta G naught is a reaction dependent on mechanism. Delta G activation is a reaction dependent on mechanism. The delta G naught is a reaction that may change by adding a catalyst. And it says the bigger the delta G, the faster the reaction. The bigger the delta G, the slower reaction. Now, think about the equation. What do you guys get? What do you guys think? It was not E, yeah. I kind of set you guys up, didn't I? Okay, so the correct answer is B, right? The reason why the correct answer is B is because we can couple reactions to get them to go faster, right? So in other words, we can set the path of a reaction so that it can go faster, right? Or that delta H, that activation, is going to be dependent on the mechanism of the reaction. Okay. Does that make sense? So the correct answer is B, because the delta G for activation of the reaction is going to be dependent on the mechanism. So we can change the path of a reaction by coupling, right, with another reaction. So you saw like earlier where we had the endogonic part of it coupled with the exogonic. So we can speed up reactions, that activation energy, by adding layers to it, right? We don't have to go. So do you guys remember we talked about state functions in 1B? State functions, it basically says, and we primarily talked about it in terms of, or actually we talked about it in 1A, and we talked about it in 1B. We talked about it in terms of Gibbs free energy, and we also talked about it in terms of enthalpy, right? So I can get to the same point in one step, or I can get to the same point in multiple steps. Yes, yeah. So we can actually couple a reaction so that that energy, that delta H of activation, is lower than what we need by coupling two reactions together, okay? By using a different state function. The outcome is going to be the same. We're going to get that product, right? The energy has to add up to the same towards the end, but that activation we can play with by the path that we decide to go, right? So I could sit there and have you walk all the way around a mountain to get to the top, right? Or I could have you go straight up that mountain to get to the top. Or I could have a helicopter take you to the top and then just drop you down, right? So the outcome is going to give us the same, right? It's just the way that we go, right? Okay. Yes, well, a catalyst is, yes, going to cause speed up that reaction, and it's also going to affect that activation energy. That's right. So it's dependent on the mechanism. Okay. Make sense? The correct answer is B, as in boy. Okay. Okay. So we will pick up kinetic and thermal stability at our next lecture.